Hi everyone, welcome to the third part of the video. In this part, we will dive into the second proof technique, proof by counterexample. Here is an overview of what we will cover in this part. We will first go through the definition of what is a counterexample and then go through actual examples. The idea behind this technique is that I give you a statement and say in all cases, the statement holds true, and you will say no to me by presenting me a concrete case where the statement is not true. The main difference between proof by contradiction and proof by counterexample is that the counterexample can only prove statements as false. On the other hand, as we've seen in the second part of the video, proof by contradiction can prove statements either true or false. Let's go through an example. For every n greater than 0, f of n equals to n is always greater than g of n equals 2 to the power of 10 times log base 2 of n. To have a better understanding of what the functions look like, here is a graph, where the green linear line is f of n and the purple curved line is g of n. For this problem, we have restricted our cases to only n bigger than 0. Now, you will have to come up with a case, or n value, that proves f of n equals to n is smaller than g of n equals to 2 to the power of 10 times log base 2 of n. You may pause the video and come up with possible cases. Well, hope you did come up with one counterexample. Just by looking at a graph, we could see that the shadowed part are the potential solutions for n that is a counterexample. So let's just go with the easiest number 2 to account for the log. When the case is n equals to 2, function f will just be 2, and function g will be 2 to the power of 10 multiplied by log base 2 of 2. Log base 2 of 2 is just 1, so function g evaluates to 2 to the power of 10, or 1024. Obviously, 2 is less than 1024, implying we have just found a counterexample at n equals to 2 where the function f did not grow faster than function g. By providing just this one counterexample, you have enough proof that the whole statement is false. Now let's consider a hard example. For every n greater than 1, f of n equals n is always less than g of n equals to 2 to the power of 10 times log base 2 of n. This means, essentially, we want to find a counterexample that falls in the case where f of n is always greater than g of n. Before aimlessly trying to find a counterexample, let's use what we have just learned and justify whether a counterexample can be found for this statement. Even though the graph looks like f of n equals to n is always greater than g of n equals 2 to the power of 10 times log base 2 of n, when n gets infinitely large, we still want to use the limit rule to confirm so. We have the limit of n to infinity of n over 2 to the power of 10 times log base 2 of n. The log in the limit seems to be a problem. However, we can use the L'Hopital's rule to evaluate the limit. The rule says that we could do derivative to numerator and denominator separately, then compute the limit using the derivatives if the limit exists. The derivative of n is just 1. The derivative of 2 to the power of 10 times log base 2 of n may be a little bit complicated. The constant 2 to the power of 10 remains during the derivative, and the log base 2 of n follows the rule that the derivative of any log base a of n is 1 over ln a times n. If you want to look more into these two rules we used, you may scan on the corresponding QR codes. From this, our denominator evaluates to 2 to the power of 10 over n times ln 2. Our whole limit now looks like limit of n to infinity of 1 over 2 to the power of 10 divided by n times ln 2. This means that we can just switch the positions of numerator and denominator, and we have n times ln 2 divided by 2 to the power of 10, or n times ln 2 divided by 1024. Since ln 2 and 1024 are all constants, and n is left at the numerator, this means that the limit approaches to infinity. This also means that f of n equals to n is indeed asymptotically greater than g of n equals to 2 to the power of 10 times log base 2 of n. Or asymptotically, g of n equals small o of f of n when n gets large enough. We can indeed also find an n value that shows f of n is always greater than g of n. One can technically stop the proof, since the limit of f of n over g of n is infinity shows that there exists a counterexample. However, this might not be as satisfactory as giving an explicit counterexample. You may pause the video and come up with possible cases. Well, hope you did come up with one counterexample. One could also do an eyeball on the graph and select potential n values. However, to make it simpler, we'll use n values with powers of 2, but much larger. Let's just take n equals 2 to the power of 10. F of 2 to the power of 10 is 1024, and g of 2 to the power of 10 is 2 to the power of 10 times log base 2 of 1024, which is 1024 times 10. This gives us g of 2 to the power of 10 equals to 10,240. 1024 is indeed less than 10,240, which means f is smaller or less than g, making it not a counterexample when n equals to 2 to the power of 10. Let's try something even bigger. N equals 2 to the power of 20. F of 2 to the power of 20 is just 2 to the power of 20, but g of 2 to the power of 20 is 2 to the power of 10 times log base 2 of 2 to the power of 20. This gives us 1024 times 20, which is 20,480. Finally, we have found a case where f of n grows greater than g of n, and that is when n is 2 to the power of 20. We have now finished all of our parts on asymptotics, limits, proof by contradiction, and proof by counterexample. If you have any questions, do not hesitate to post them on Piazza or come to our office hours.